Let's see where we left off at. I think we finished this up, yeah? You need to be working on those, asking questions, like I said, reference rules. Charlie Brown on the back, and who's that? Dennis the Menace. Something to take a look at about residents. We have a new handout, mass spec. We'll do one on this and one over here, it's the same thing. But right now we're going to move on to the tan sheet, which is the chemistry of dienes. Dienes. Double the fun, kind of like alkynes. We're going to have two enes, called a diene. There's a little warm-up sheet there. Some questions. Chapter 17. First thing, conjugated, non-conjugated, and accumulated dienes. We actually have already covered that. That was on the residence page. Let's look at nomenclature of dienes. All nomenclature is very similar. This compound here, longest continuous carbon chain. 1, 2, 3, 4, 5, 6, 7. So this is going to be a hept. If this was just one double bond, it'd be a heptene. With two double bonds, now this is difficult. It's a heptadiene. Heptadiene. But you have to say where the double bonds are at, because that there is also a heptadiene. First carbon of your double bond gets is the number you use. What's going to be the one in, on the right or left?
Right.
Correct. This is going to be 2, 3, 4. I drew this here. That's a 2,4 heptadiene. What is this here? 2, 3, 4. 2, 6? 1, 5. No. 1. 1, 5 is better than 2, 6. This is a 1, 5 heptadiene. So you just put the positions of your double bond using the first number of the alkene location. We have something else with these. We have E or Z. Don't forget that when possible. Is the two double bond E or Z?
E. I meant E.
E. E for opposite, trans. How about this one?
E.
Yes. So the first one would be E, comma E, 2,4 heptadiene. What would you want to put in front of 1, 5?
Just 1 E.
E, 1, 5 heptadiene. That doesn't have any E or Z. So you only need one E. E obviously means this one, because that one doesn't have E or Z. Now, they're both E, so we don't have to use any number to say which is which. If one was E and one was Z, we would have to say maybe 2E for Z or something. Maybe that'll come up over here. What do you want to call this guy on the right? 1, 2, 3, 4, 5. Hey, that's also a heptadiene. What's the double bond positions? 2, 4. So we also have a 2, 4 heptadiene. What's the difference between this 2, 4 heptadiene? That one's Z and this one's E. So we can say 2Z, comma 4E Pretty straightforward. Name this guy here. Longest continuous chain. 1, 2, 3, 4, 5, 6, 7, 8. Double bonds have to be included, just like alkenes. Double bond has to be included. Might as well start right here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Hexadiene. What are the numbers of the hexadiene? 1, 2, 3, 4, 5, or 1, 5, or 1, 5. Either way you go, you get 1, 5. How do you want to decide? Give subs lowest numbers. If that's 1, chlorine would also be 1. If we're here, the subs would be higher numbers. So I'm going to say this is 1 and that's 5. 1, 5 hexadiene. What's on that? I have a chlorine and a propyl, alphabetical order. 1 chloro. 2, what's at the 2? 2 propyl dash 1, 5 hexadiene. Do we have potential for stereochemistry? Not here. What about here? What is this? Z. Chlorine and the propyl are on the same side. Z, 1 chloro, 2 propyl, 1, 5 hexadiene. How does that look?
Why wouldn't it be E? You wouldn't include the
Yeah, you're exactly right. It would be. Going too fast. Chlorine is 1, H, which is better. I don't know why I just said this. Carbon's the same, carbon's the same. This carbon's bonded to 3 H's, this carbon's bonded to 2 carbons. Exactly right, very good. E. Who else noticed that error? Why didn't you say anything?
I did, but I think you said Z over it.
Good, yeah, that'd be E. Okay. Nomenclature of dienes. What if you had three double bonds in the compound? 3. Heptatriene. Tetraene. We're pretty much just going to name dienes. Okay. Addition reactions of conjugated dienes. This is conjugated here. Just like adding HBr to an alkene, we can add HBr to a diene. What we're going to see is some different possible outcomes. We're going to have some terminology. 1,2 versus 1,4 addition. 1,2 addition is also called direct addition. We'll do an example here. Direct addition is just like we've been doing for the past month. Really not much difference other than which alkene are we going to start with. We've got HBr. Temperature will be important. If you take this conjugated diene, react with HBr, you can get this addition product. How does that happen? Well, apparently, you see that new H there? We're adding HBr across this pi bond. Now, first off, which pi bond are we going to react with if you didn't see product? They're the same. This is a symmetrical diene. Either one you can use, you get the same product. It's a symmetrical molecule here. I'm going to do it over here because that's what I give product here. I've got H plus, Br minus. These electrons can attack H plus. Where are we going to leave cation? Left or right? Correct. So these hinge away, make bond, leave cation there. Hinge away, make bond, leave cation there. But that's got that. Plus charge. So there's your rate determining step for adding the proton, get the carbocation intermediate. How do you get final product? Same old thing, Br adds here, final product, right? It's like we ignored the other double bond. That's called a 1,2 addition. Why? Because the H is here on this carbon, and the bromine ends up not on the one carbon, but one away on the two carbons. That's not nomenclature. This could have other carbons. It's the relative positions of the H and the Br. One is here, the other one is right next door. 1, 2. Later on, we're going to see 1, 4. Where the H is here and the bromine ends up not on 2, not on 3, but it ends up out here on 4. This is a 1,2 addition, also called a direct addition. Good old standard addition like we've been doing for a month. Here, this is the kinetic product because it's formed fastest and thus always first. When is it first? Always. Okay, we will contrast this with thermodynamic product when we get below. Why is it formed fastest? We'll come back and answer that. Cold temperature is very important. We'll learn that cold temperature gives kinetic product. The 1, 2, what is the kinetic product? Right there. The 1, 2 product is the kinetic product. A lot of this will become more clear when we do another example, and you can see what we're talking about when we do another example. Now, on the other hand, if you do the same reaction, same molecule, same reactant, but you do it at higher temperature, not cold. By the way, why do we say minus 78? Why didn't I say minus 72 or 74 or something? What's special about minus 78? If you put dry ice and acetone, it will achieve a temperature of minus 78. So that's why reactions are often done at minus 78. Not because that's a great temperature, but that's because that's what you get when you put dry ice and acetone. It's like doing a reaction at 0 degrees. That's what you get when you put wet ice in water. Okay? So that's dry ice acetone temperature. If you do it at higher temperature, like about 40 degrees or higher, you get another product. Not the 1, 2 product, but the 1, 4 product. 1, 4 addition. This is called conjugate addition. If you look at here, the new H is where? 2 on the end, there's now 3 there. The new H is here. And if we call that 1, where's the bromine? It's on the 4 carbon compared to the 1 carbon. That's a 1, 4 addition of HBr. This is called the thermodynamic product. Why is it called that? Because it's the most stable. Kinetic product implies rate. Kinetic product is formed fastest. Thermodynamics implies stability. This is the most stable. This product is more stable than the one above. Let's answer that. Why is this product more stable than the one above?
More substituents and double bonds.
Doc, these are both still alkenes. How do you judge alkene stability? More substituted, the better on the double bond, right? This up there, the double bond has one carbon substituent. How many does this double bond have? Two. They're isomers otherwise. More carbon substituent on the alkene, more stable. Okay? This is more stable. It's called the thermodynamic product compared to the 1,2 product. But is it formed fastest? And this first? No. Actually, the less stable products form fastest. Why does cold temperature only give that one, but higher temperature gives this one? We'll talk about that. Before we move on, let's do the mechanism for this. How do we get the bromine out there? Hopefully you already see this. It's a big word, starts with R, and then an E. Resonance. H+. Electrons come out. UH here, cation here. That's the same intermediate as above. Same intermediate. But what did we not talk about above? We didn't talk about this cation is resonance stabilized. Same as above, I just didn't talk about it. Show resonance of this cation. Resonance arrow, how do you stabilize the carbocation? Move electrons towards it. Do we have any electrons? Do we have a lone pair or a pi bond that we can move towards it? Windshield wiper, boom. What does that give? Pi bond there, and plus on the end. That Br is sitting here. How do you then get the final product, final 1,4 product? Br doesn't add here. If it added here, you'd get the 1,2 product. Instead, it adds where? There, and that gives final product. This is an example where the nucleophile adds to a different cation other than the original. Because this was conjugated, it was able to add out there. That's why it's sometimes called a conjugate addition. How many intermediates do I have in this mechanism? One. Very good. These are both fake. The true structure is what? The true structure is a hybrid that has bond and a half, partial plus, partial plus. That's the true intermediate. Question, Sarah?
Can we call them anti-Markovnikov?
Anti-Markovnikov? No, not really. Anti-Markovnikov would be where we put carbocation here and bromine added here. We're doing standard chemistry. We put cation where we should have. What's added on here is resonance.
Okay, I see that.
We're not doing anti-Markovnikov. It's standard, we just have resonance added in. Here's the true intermediate. At this point, see, this is the same intermediate we had above. I just didn't draw resonance. And Br minus, you see you have two partial pluses. Br minus could add here or here. If it adds there, you get the 1,2 product. If it adds there, you get the 1,4 product. The problem is, if we add here, how do you deal with these partial electrons? This gets very cumbersome. Instead, we work with the fake structures, and we can add here to give that one, or here to give the other one. But these are fake structures. But in real life, it's either adding here or here. And both carbons are partial plus, so the bromine is attracted to either one. Well, why do you get 1,2 formed fastest and this formed? We already know why this is most stable? We answered that. Why is the 1,2 form fastest? Let's answer that. When this attacks the H+, where's the Br- at this point? Is it way over here, or is it sort of next door to the plus? Do you think the Br- and the H+ are close together? They are. Yes, they're ionized and separated, but these ions still have attraction. Right there. And thus, when this happens, the Br- is about right here. It's close to this H. Now, at this point, which is going to be faster? This adding here, or this going across country and adding there? Which would be fastest? Boom. That's fastest. That's called a proximity effect. It's just closer to there. That's why you get that one fastest. Doc?
Will that always give us our major product?
Depends on temperature. We got to keep addressing different things. Right now, just address why it's faster. Does it make sense why this is faster here? This is actually activation energy. Not just, boom, it's closer. Which takes more energy? For me to walk right here, or me to walk way over there? Boom, walk right here. That means that's a lower activation energy to add here, because it's closer. But, does adding here give you the most stable product? No, it doesn't. We already said this is the most stable product. Okay, when you're under cold temperature, you don't have a lot of energy. And you just kind of add here. Cold temperature, you don't have enough energy to go over there. When you're under higher temperature, you have more energy. And this is where we're going to have to look at a reaction coordinate diagram. And with higher energy, you can make it over there. But hold on. Which happens first? You always add here first. So we have to look at this some more. Let's look at the next page. Well, there's a couple of things. Let's look at this diagram, and then we're going to look at an actual reaction coordinate diagram. Here's the temperature. Here's the reaction with temperature thrown in. If you do HBr with low temperature, you're going to get the 1,2 product, called the kinetic product. Actually, I think we should look at the next one first. Turn over one more page and let's look at this first. Actually, when we first looked at reaction coordinate diagrams, the same diagram was in the packet. This is the same exact reaction. Here's your diene and a kind of a condensed form of the structure. We start here. We attack and we get a carbocation. Here's a carbocation here, the common intermediate. This is your resonance stabilized cation. Right here, common intermediate. From there, you can get the 1,2 product or 1,4. 1,4 is more stable, so it's lower. 1,2 is higher. So that's your thermodynamic consideration. For each, there's a transition state. Which takes less energy? Adding 1,2 or adding 1,4? Which takes less energy? 1,2 takes less energy. So look at this. Here's the 1,2. You see how it takes less energy to get to it? Illustrated here. That's proximity effect. It doesn't have to travel as far. Lower. So, which is going to form first? Forming first is a kinetic, not thermodynamics, kinetic rate. Water doesn't run uphill if it doesn't have to. Water's energy is going to go here, and you're going to get the 1,2 product. Now, if you're at cold temperature, you don't have enough heat to make it over there. You have to go this way. And you come right here. You get the 1,2 product. So how do you get to 1,4? With heat, you can get to 1,4. Why with heat? Because with heat, what actually happens is you can reverse this back up here with heat. And if you got enough heat, you can then make it go over this hump and fall here. Of course, you can reverse this back up and come here. Basically, with heat, you can now go back and forth. With heat, you now have an equilibrium. And when you have an equilibrium, how do you judge equilibrium? Most stable. And so this achieves an equilibrium. Most stable is then preferred, and you end up with the most stable. But see, if it's cold, you can't achieve an equilibrium, because if it's cold, all you can do is go over here and you're stuck there. Question?
So does the extra energy initiate resonance then?
No, you never initiate resonance. Resonance is something we do on the board.
Okay.
Resonance is just always there. As soon as the intermediate is formed, it's pink.
Okay.
I showed red and white. We just have to know as soon as the intermediate is formed, it's pink. As soon as it's formed, it's this. The heat allows it to reach equilibrium, and you end up with the most stable. Without heat, it just stands here, because that's all it can do. It doesn't have enough energy to do anything else. Now this is summed up, what I was trying to show here. I think this is kind of the summary. Low temperature, kinetic product. Game over. That's it. If you have heat, you can keep going. This thing can actually reverse. And what's happening here when it reverses? The BR has to just leave. I mean, to get the BR to get this product, we added here. But a BR can just turn around and leave. What's that process called if a leaving group just leaves? And it forms this plus what? BR minus. What's that process called? It went from a neutral to 2 ions. Ionization. Have you ever seen anything ionized? What happens with HBr if you put it in water? The Br leaves and you get H plus Br minus. Right? Ionization. Yeah. With heat, it'll cause us to ionize. Of course, here's red and white. The true structure is pink. Then the Br could add over here and get that product. Of course, this can ionize and come back. See, at this point, this is all equilibrium. And when you achieve an equilibrium, which is favored? Most stable. That's the most stable with heat. That's what you get with heat. Leaving group. We'll see a lot more of this going forward. This is just where the leaving group just up and leaves. Ionizes off. Okay, did we answer everything? Cold temperature, warm, think about it. Let's see if we can do some problems here. This diene is not symmetrical. This double bond is different from that one. That one has a methyl on it. In this case, we've got to decide which double bond are we going to react with. HCl, just like HBr. Cold temperature. Okay, cold temperature. Which product are we looking to make? 1, 2. Good. Let me ask you this. If this was heat, which product would we be looking to make?
The most stable.
The most stable. In my example, the 1,4 was most stable. 90% of the time, the 1,4 is most stable, but not always. The answer to heat is most stable. Usually 1,4, but not always. What do you get with heat? Most stable. There you go. Okay, cold temperature is always 1, 2. Because boom, 1, 2. It's easier to do 2. Faster. Do it 1, 2. Question is, which alkene are we going to react with? You're going to react to get the most stable carbocation. If we react over here, I would get H here plus here. We got to consider resonance because that's part of this argument here. The resonance over here windshield wiper plus, is that the resonance structure? The true structure of this, we can call the blend, the hybrid, but we can also say this. This cation has characteristics of secondary and primary. Secondary cation, primary. What if I had reacted the other pi bond? I would react it this way. By the way, it's always going to be in the middle. Cation is either going to be here or here originally because resonance. If cation was out here, you would be able to do resonance. If we go this way, we would get UH there plus here. Is that right? Resonance would do like this. I'll draw it up. Here and here. Is that resonance? What types of cations do we have here? The blend is going to consist of tertiary and primary. Which cation is better? One that has primary secondary characteristics or one that has primary tertiary characteristics? Yes, this is your better cation. Thus, at this point, get rid of the other one. Because you're going to form the best cation. And that has nothing to do with cold or hot temperature. You're going to get the best cation. That's your best intermediate. It's a common intermediate. Now the question becomes, is the Cl minus going to add to this carbon or this carbon? Well, cold temperature is 1, 2. Which carbon is it going to add to? There's 1, there's the new H. I'm going to add here. Boom. And so the product is which one of those over there? Yes, the product is right there. 1, 2 addition, but importantly using the best alkene because this was the best intermediate, best cation. Identify the other 3 in terms of terminology. 1, 2, 1, 4. What type of product is this? Or this. Where's the 1, 4 product for this reaction? If this was heat, which product would be formed? Same cation. This is going to be formed either way. But with heat, you would get the most stable product. Would it be double bond there or around here? Alkene with one group or disubstitute alkene? Yes, chlorine would be out here. Which product is that? Hold on. I'm missing a carbon on this one, aren't I? And there's supposed to be a carbon there? Which one is that? Yeah, with heat would be that. These two come from reacting the other alkene, but as we said at the beginning, we're not going to react the other alkene. So if this was heat, we would get that, and that would be a 1,4 because the new H is out there and the chlorine's here. 1,4. Okay, do the second one on your own there. Take a minute to do that. First, have to determine which alkene is going to be the reacting one, because this is not symmetrical. These alkenes are different. Which alkene are we going to react with? If we react here, I would give carbocation here, which would be tertiary resonance. We put it here, secondary. So I see secondary, tertiary. If we reacted here, cation there, that'd be secondary. Electrons over, that'd be primary. Secondary, primary. Which is better? First one. Electrons here. H added out there. Plus there. Basically, with cold temperature, you don't really have to consider resonance. It's not a conjugate addition. It's a direct addition. With heat, you have to consider resonance. Because when you consider resonance, you show what a possible 1,4 addition would look like. Resonance would be windshield wiper over, resonance arrow, now I have double bond here, plus there. Okay? Do you want to have a final product with the chlorine that's attached there or there? Chlorine under my hand there. If the chlorine was under my hand, what type of alkene would that be in terms of substitution? Why is that slow, guys? What type of alkene is that in terms of substitution? How many carbon groups on that alkene? 3. Tri-substituted alkene. If the chlorine was under my hand there, what type of alkene would that be? Di-substituted. Which is more stable? Tri. Heat gives more stable. Tri. You want chlorine to add here. And so in terms of mechanism, you add here, you get final product. I reckon I'll draw it. Chlorine added there. The new H is here. The new H is on 1, 2, 3. The chlorine's on 4. with heat, there's your product. If this was cold temperature, you would draw a product with chlorine here, 1,2 product. Because the chlorine would be able to add there fastest. Because remember, the chlorine is near the H, boom, it adds there fastest. It has to go cross country to get to the 1,4 product. This is a higher activation energy, but you get a more stable product. How does that look?
It has iodine.
Thank you. This was iodine. Was that what the bewildered looks were about? HI. I minus. Okay. There's a couple of more, 4 more to do on your own. The answers to these are included in the handout. It's a few pages over. It's flipped upside down so you won't accidentally look at the answers. Please work on these. Okay? And we've made it to the Diels-Alder reaction. Diels-Alder reaction, one of the top 10 reactions in organic chemistry. I'll say that for about 20 different types of reactions. Diels-Alder won a Nobel Prize in 1950. I think one was a professor and one was a student or something. Working together, they developed this reaction. Or maybe that was the Friedel-Crafts reaction. Friedel-Crafts. I get them confused. Diels-Alder, very important. First thing about Diels-Alder is you have to be able to add 4 plus 2 equals 6. Okay? That's the first part of it. Diels-Alder involves a diene. There's a diene, conjugated diene, reacting with an alkene. Now there's 2 alkenes here, but that's just an alkene. Okay? That is basically, this is 4 carbons. And then you got 2. And 4 plus 2 gives what size ring? 6. Diels-Alder gives a 6-membered ring, a cyclohexene. Cyclohexene, 1 double bond in the ring at least. You might have more double bonds, but it's got to have at least 1. 4 plus 2 is 6. Cyclohexene. 1,3-butadiene, that'd be the name for that. This is the most simple of a Diels-Alder. More common is for these core components to have things bonded to them. Decorations. But ultimately, you're going to get this with, decorations on it. You can also react a diene with an alkyne. That would give cyclohexene with an additional pi bond in it. We'll see why. In this process, this is called the diene. This guy loves dienes. What do you want to call this guy? A dienophile. Okay? It loves dienes. Just like an electrophile loves electrons. So you have a diene and a dienophile. The dienophile is a pi bond. Usually an alkene. Could be other pi bonds. It could be a carbonyl or a C double bond N. Mostly for us, it's going to be carbon-carbon alkene. Mechanism for this. It's a concerted mechanism shown with arrows here. I'll do it fresh. You got this. You got this. Let's first look at p orbitals. it's really all these p orbitals start interacting. Because you got these 4 p orbitals here. One electron making pi bond, one electron making pi bond. Of course, you got pi overlap here. That's conjugation. We've talked about that. This guy sort of approaches this, and I'm going to draw the p orbitals this way. I mean, these can be like this or this. They got to overlap. You got this here. There's your pi bond there. What happens is this approaches and this starts overlapping. And that starts overlapping. Now, this is not just all conjugation because it's 2 different molecules. You're doing a reaction here. These approach, and the transition state sort of looks like this. And a book may show a transition state. Now, what happens is you get reorganization of the pi electrons, and boom, you end up with product. You end up making bonds. In terms of arrow movement, it's usually done like this. These electrons sort of windshield wiper over and make bond there. Something has to leave this carbon because it can't have 5 bonds. These electrons sort of windshield wiper from down here over there and make bond over there. Well, something has to leave here because it can't have 5 bonds. Well, since these electrons left, this carbon needs electrons. And so these can just windshield wiper down. All that happens at the same time as these come together, what does this arrow movement give? Gives that right there. Now these arrows are just sort of went the other way, but it's the same thing. Because right here we're making single bond here. Single bond. This pi bond is breaking, leaving that as a single, but it's making single up there. But importantly, what is this here moving down to make? When that moves down, you got a double bond here. And so there's that double bond. Thermodynamics, kinetics. Is this reaction favored kinetically? 2 molecules going to 1. Is that favored kinetically? I don't know why I'm saying kinetically. I should be saying entropy, entropically. Entropy. Is this reaction favored by entropy? 2 going to 1. No, it's not. Not favored by entropy. So would you want to heat this reaction? Would heating it make it go? Who knows? Heat amplifies entropy. Entropy is bad. You're going to amplify a bad term. How about thermodynamically? Is it favored thermodynamically? What's going on there? You take stock of this. I've got 3 pi bonds. It's kind of 3 pi bonds all doing this reaction. And these 3 pi bonds become what? Two sigma 1 pi. Which is better, 3 pi bonds or 2 sigma and 1 pi? We're getting better. Stronger bonds. So is this favored thermodynamically?
Yes.
Yes, it's favored thermodynamically. But not entropically. Okay, we're about out of time. Let's see. Please look ahead on the Diels-Alder. We're going to have non-symmetrical. We got. How do you deal with non-symmetrical dienes? What does S-cis mean? Then we're going to have stereochemistry. Please look at the stereochemical outcomes. Problems to attempt over here. And then there's some application pages. We'll finish up Diels-Alder pretty quickly next time. Please look ahead, see if you have questions. Write them down. Then we'll be moving to mass spec. I gave you that handout today. In lab this week, we're doing the hydration of the alkyne. We may be able to do mass spec near the end if a group gets done quickly enough. Otherwise, this is a 2-week lab, and next week we'll be doing mass spec on the product you make this week. SI today at